In last video, we discussed about the electronic configuration of lanthanides, and at the end of video, we were discussing about the properties of lanthanides, and some of the properties of lanthanides depends upon electronic configuration, and these properties are oxidation states, lanthanide contraction, then magnetic properties, spectral properties, as well as the complex forming ability of the lanthanides. So in this video we are going to discuss these some important properties. The first property of lanthanide is oxidation states of lanthanides. Now lanthanides have a +3 oxidation state as a common oxidation state. When it loses 2 electrons from 6s orbital and 1 electron from either 5d orbital or 4f orbital, then its oxidation state becomes +3. And all the lanthanides have common stable oxidation state, that is the +3. Now in addition to +3, some lanthanide shows stable +4 and +2 oxidation state. For example, cerium shows +4 oxidation state as a stable oxidation state. Reason for this is when this cerium loses 2 electrons from 6s orbital and 2 electrons from 4f orbital, then its configuration will be 4f0, 5d0, 6s0. That is, it acquires the xenon gas configuration. That configuration is highly stable, and therefore cerium has +4 oxidation state. Similarly, terbium also shows +4 stable oxidation state. Reason for this is to get +4 oxidation state, when terbium loses 2 electrons from 6s orbital and 2 electrons from 4f orbital, then its configuration becomes xenon 4f7, which is again stable electronic configuration. So cerium and terbium shows +4 oxidation state. Similarly, europium and ytterbium, these two elements shows +2 stable oxidation state. When europium loses 2 electrons from 6s orbital, then it acquires electronic configuration like xenon 4f7, which is stable electronic configuration. Similarly, when ytterbium loses 2 electrons from 6s orbital, then it acquires configuration like xenon 4f14, which is also stable electronic configuration, and therefore europium and ytterbium, these two elements shows +2 oxidation state in addition to +3. Similarly, neodymium shows +2 and +4 oxidation states. Promethium shows +4 oxidation state. Thulium shows +2 oxidation state in addition to common +3 oxidation state. Now cerium, as I said, its observed configuration is xenon 4f2, 5d0, 6s0. In +3 oxidation state, the cerium +3 has a configuration of xenon 4f1. Samarium in +3 oxidation state has a configuration of xenon 4f5, and ytterbium in +3 oxidation state has a configuration of xenon 4f13. So this is for cerium. In +3 state, it has configuration xenon 4f1, whereas in +4 oxidation state, it has configuration xenon 4f0. Europium in +3 oxidation state has a configuration xenon 4f6, whereas in +2 oxidation state, which is stable one, has a configuration of xenon 4f7. Terbium in +3 state has a configuration of xenon 4f8 as I explained here. In +3 state, it loses 2 electrons from 6s orbital and 1 electron from 4f orbital, and therefore its configuration becomes xenon 4f8. In +4 state, its configuration will be 4f7. Ytterbium in +3 state 4f13, +2 state 4f14. Neodymium in +2 state has a 4f4 and in +4 state 4f2. Samarium in +2 state has a configuration of 4f6 and in praseodymium in +4 state has a configuration of 4f1. Thulium in +2 state has a configuration of 4f13 and dysprosium in +4 state has a configuration of 4f8. So these are the configurations, electronic configurations in different oxidation states of lanthanide ions. Most important thing is their common oxidation state is +3, and cerium as well as thulium shows +4 stable oxidation state, and europium and ytterbium shows +2 stable oxidation state in addition to common +3 oxidation state. Now stability of oxidation state, it depends upon stability of resulting electronic configuration and thermodynamic factor. So not only stable electronic configuration decides the stability of oxidation state, but also thermodynamic factor plays very important role in the stability of oxidation state. For example, the tripositive lanthanide ions are more stable than dipositive or tetrapositive lanthanide ions in aqueous solution. This is due to favorable enthalpy of ionization and enthalpy of hydration. It means lanthanum +3 ions, these are highly hydrated, and because of high enthalpy of hydration, +3 oxidation state is more stable in aqueous solution. Even enthalpy of ionization, this is also favorable in +3 oxidation state. In solid state also, enthalpy of ionization and lattice enthalpy of the +3 ions are more negative, and therefore tripositive ions are more stable in solid state also. And the stable lanthanide complexes in +2 and +4 oxidation states are cerium chloride, especially cerium dichloride, cerium dioxide, promethium dioxide, and neodymium iodide. In cerium dichloride, oxidation state of cerium is +2. In cerium dioxide, its oxidation state is +4. In promethium dioxide, its oxidation state is +4. And in neodymium iodide, oxidation state of neodymium is +2. So these are the some important lanthanide compounds in which the lanthanum ions have +2 and +4 oxidation states. Now next point is lanthanide contraction and its consequences. In lanthanide series, with increase in atomic number, there is a progressive decrease in atomic as well as ionic radii of trivalent ions from lanthanum +3 to lutetium +3. This is called lanthanide contraction. Now consider this graph when atomic number is plotted versus ionic radius of the lanthanide ions. Then from lanthanum +3 to lutetium +3, the ionic radius of tripositive ion gradually and steadily decreases. Not only for +3 ions, but for +2 as well as +4 ions, there is a gradual decrease in ionic radii. So this is called as lanthanide contraction. Now what is the reason for this? Now from lanthanum to lutetium, atomic number increases by 1 unit, and therefore number of protons are progressively added in the nucleus. At the same time, the number of electrons in 4f orbital, these are also progressively added. So number of electrons are added in same shell, and number of protons in the nucleus also increases. So positive charge increases, at the same time the negative or the negatively number of electrons in the same shell also increases, and therefore shell becomes compact and compact, and therefore from lanthanum plus 3 to lutetium plus 3 there is a gradual decrease in size. And as I said, this lanthanide contraction, it is due to increase in nuclear charge. Nuclear charge means number of protons present in the nucleus. It is also due to the progressively addition of electrons in the same 4f level, and there is a force of attraction between these electrons and protons, which causes the contraction in size of the shell. And one of the reason for lanthanide contraction is less screening effect caused by 4f subshell. Actually the order of screening ability is S subshell has highest screening ability as compared to P, then D, and F subshell has lowest screening ability. So because of less screening effect caused by 4f orbitals, the impact of protons, positively charged protons, on the electrons progressively added in the shell, outermost shell, is more. If screening effect is more, then because of this screening effect, the protons and the outermost electrons, in between them there will be some sort of shield or screen which decreases the force of attraction between protons present in the nucleus and outermost electron. But here, because of less shielding effect or screening effect caused by 4f subshell, the shell becomes, or there is a more impact of protons on the outermost electrons, and therefore total result of this is there is a decrease in size of lanthanide ions from lanthanum to lutetium. Now it is observed that ionic radii decreases from lanthanum to lutetium. For lanthanum in picometer it is 117 picometer, and for lutetium the size is 100 picometer. So approximately there is a decrease in 17 picometer size. It is in picometer. So this is called as lanthanide contraction. And in nanometer, from lanthanum to lutetium, there is a decrease in 0.02 nanometer size. Okay, so this is what is lanthanide contraction. So remember, lanthanide contraction means in lanthanide series, with increase in atomic number, there is a progressive decrease in the atomic as well as ionic radii of trivalent ions from lanthanum plus 3 to lutetium plus 3. This is called lanthanide contraction. Now the consequences of lanthanide contraction, or what are the effects of lanthanide contraction on their properties, we are going to discuss in next video.